Hey there, calc folks, back here with another quick video. I always starting to have it tickle in my throat. Another quick video on the study of vector valued functions here, where we are going to now look at what is known as the principal unit normal vector, right? And we're familiar with the unit tangent vector, which is a vector tangent to our vector valued function or our vector valued curve, right, at points along the curve, right? It does describe forward motion if we were looking at the case of forward motion or the case of motion in space in our study, folks. It would be the direction of forward motion, right? But there also exists a description to go along with tangential behavior known as the description of normal, orthogonal, or what we might say is perpendicular behavior, right? And being described by what is known as the principal unit normal vector, all right? The principal unit normal vector is given in the following definition, right? Given r bar equal to r bar of t in r sub n, given some vector valued function in r sub n, a smooth parameterized curve for any parameter t, the principal unit normal vector denoted by n bar, right, is described by, let me get my lights fixed there, is described by the calculation seen here. Now, I should have maybe been a little bit more specific here. This is where t bar of t, right, equal to the ratio given by r bar prime of t divided by the magnitude of the r bar prime of t. Right, is the unit tangent vector, right, to r bar, right, at any parameter t, right? So let's get a little bit more specific there and just make sure we denote that this value of t bar that we see in our calculation here, where we are taking the derivative of that function, right, does involve that unit tangent vector, right? And we see that occur here, right, in our calculation. All right. Now, let's look at an example here. These are never necessarily fun calculations, and I do encourage you, if you can use a program like Mathematica to perform these, that will always make your life a little easier. But before we actually get into a calculation, I see here that what we have to look at is a little bit of theorem here. Theorem related to interpretation. All right. Letting t bar and n bar describe the unit tangent and the principal unit normal vectors for r bar, a smooth parameterized curve in n-dimensional space. The vectors t bar and n bar are orthogonal at all locations along r bar. That is, at any given location, right, along r bar where we can calculate t bar and n bar, right, if we take their, now this is a dot product calculation of those two values, it will always give us the scalar result of 0 with that dot product, right? Implying orthogonal behavior between these two vectors, right? Implying that they have a 90-degree relationship to each other in space, right? Furthermore, the principal unit normal vector n bar points into the curve, right? In the direction of the turn along the curve, right? Which really has a defined value when we start to think about moving in three-dimensional space and actually curving in 3 dimensions. What would be our actual direction of turn at any given point well, the principal unit normal vector is pointing in that direction of the turn, right? And where it does get its name, folks, a lot like the unit tangent vector, it is a unit vector. It's called the unit normal vector, so it is a vector that is 1 unit in length. But then what we mean by principal is that for any tangent vector to the curve, there's actually 2 orthogonal vectors. 2 orthogonal vectors. If this is our tangent vector, there are 2 orthogonal vectors pointing off in opposite directions. The principal one is the one that points into the curve, folks. So that's where it gets that name principal from. Principal unit normal vectors. Normal in behavior, 1 unit in length, pointing into the curve. All right? That's how we interpret those values. Now, let's look at an example. Again, these can be terribly tricky at times, even for the simplest of functions. Here we see a very familiar function to us. This function r bar of t equal to t comma t squared. And we might be interested in determining the principal unit normal and the unit tangent vectors at the value of t equal to 1. All right. We do start with calculating t bar, where we have to note what is r bar prime of t and its magnitude. And those are quick calculations. 1 comma 2t is r bar prime of t, and our magnitude is the square root of 1 plus 4t squared. Implying that if I arrange those into a ratio for the unit tangent vector, I do get this result seen here. All right? So if we were at a value of t equal to 1, plugging in that value of 1 into that vector would give us this description of position, right? It would give us this unit tangent vector. It would describe the tangent vector at the position along r bar at t equal to 1. All right? And do notice, if you were to calculate the length of this vector using the magnitude calculation, you would find that it would be 1 unit in length. And then when we go back now to compare it in the end to the graph of r bar of t, we will see that tangent behavior and that length of 1 unit. All right. Now, we're going to need t bar of t to develop the calculation for n bar of t. To develop the principal unit normal vector, right? We are going to need t bar's first derivative, where you can come about that with some quotient rule or some write this here as really a product with a reciprocal function in the denominator, reciprocal of the denominator, and be able to do a little chain rule and product rule. But simplified, and I did put this together on Mathematica, we would end up with these results here. The derivative of this is negative 4t over 1 plus 4t squared raised to the 3/2 power. And the derivative of 2t over the square root of 1 plus 4t squared is 2 over 1 plus 4t squared raised to the 3/2 power. And again, I use Mathematica to calculate the norm of this result, which is the magnitude. And this is how we calculate the magnitude of this first derivative of the unit tangent vector. This is its corresponding first magnitude. Where if I arrange those into a ratio, and I did this on Mathematica again and simplified, right, I do obtain this simplified form. There is some canceling here going on, folks, with all these calculations. We end up with this simplified form here. All right? When I arrange these two results into a ratio, or if I think about multiplying this by the reciprocal of this, right, it would simplify to this statement seen here. Right? You could actually see that calculation happening above, that cancellation as you distribute through the reciprocal of this. All right? So, if we were at t equal to 1, actually I should say n bar of 1 would be equal to the vector negative 2 over root 5 comma 1 over root 5 in value. And I did say that up here. I did say t bar of 1. Okay, respectively. Now, you might see a bit of a relationship between how the values of t bar relate to the values of n bar in two-dimensional space. They are what we might think of as reciprocals of each other. If we were to think of this as a rise and this a run, right? And we were to think of this as a rise and this is a run, they would be reciprocals of each other, and with one being positive and negative for this term here, this component here, we would actually see opposite reciprocals. All right? We do see that reciprocal behavior in the normal vector, and now that's unique to two-dimensional space. All right? If we were to look at these graphically, we would see this tangential behavior and this normal behavior to the tangential. Here is our illustration of r bar of t, right? R equal to r bar of t, this parabolic curve. Here is our location at t equal to 1 on that curve. And here are the graphs of t bar of 1 and n bar of 1, respectively. All right, and this is as close to scale as I can get Mathematica to generate. And we can see that those are pretty darn close to orthogonal to one another. And similarly, if you were to look at their length on the screen and compare, or on your paper, and compare to what would be 1 unit of length along the x or y axes, you would see that those vectors would indeed be 1 unit in length. All right? T bar is tangent to the curve and points in the direction of forward motion if we were moving along that curve, the direction of forward orientation, if we were just to be generic in terms of r bar. The orthogonal vector is orthogonal to t bar, right? Orthogonal to the tangent vector. If we took the dot product of these two, if we took the dot product of this result and t bar of 1, we would get the result of 0 in that dot product, and you can see that in the calculation. And similarly, n bar of 1 points into the curve here. It is the direction of the turn, right? And this is the direction of the turn at that point in space. That is what n bar is indicating there, folks. All right? So that is the principal unit normal vector. That is its calculation. It is not the easiest calculation to come upon, you can see here. It does require a couple of rounds of derivatives and magnitude calculations for those derivatives, where you are building those derivatives up from r bar of t by looking first of all at r bar prime of t, dividing it by its magnitude to prepare t bar of t, where n bar of t is the derivative of t bar of t divided by its magnitude. All right? And at any given value of t, you can substitute into these respective functions and actually come up with these unit vector descriptions. All right? Where in the case of the principal unit normal vector, right, it will always be orthogonal to the tangential, which means their dot products will equal 0, and it'll always point into the curve in the direction of your turn, right? Which in two-dimensional spaces, you know, it's turning left or turning right, but in 3 dimensions, that turn has a lot more description to it, right? It's not only turning right, it might be turning right and up, it might be turning left and down, right? And how much are we turning left and down by, or how much are we turning right and down by, or strictly right, or strictly up, or strictly down, right? So, you know, that n bar becomes much more important in those cases, folks, also with respect to describing direction of the turn. It is pure direction, right? What would be considered our direction of the turn? All right. With all this prepared, we're going to come back now to the case of looking at what our components of acceleration, folks. That's the last little video I have for you here. Should have that out for you shortly. I hope you're all doing well, and I'll post this video up. Not too long on this one. Like I said, I'm trying to keep these brief so that they're not overwhelming, folks, in terms of time.
Here's what's new.
All right.
From the Daily Show with